Let's move on to question number 4. I'm sorry for the small writing. I'll try to figure out how to expand the board as I continue to do these longer questions. All right, so the next question is find the local maximum and minimum values and saddle points of the function, and they provide us with 2 functions again. Okay, so we need to classify what a local extremum is, first of all, okay? So a local extremum is somewhat like a critical value, but it's for mostly multivariable functions. So a local extremum occurs when the partial derivatives of f of function f. So this could be 2 variables, 3 variables, 4 variables are all 0. So when the partial derivatives of function f are all 0, that means that at that point there is no rate of change at any direction. X, Y, Z, W, U, V, how many variables you have, okay? And so not only do we need to know what a local extremum is, the question is asking us to find the local maximum, minimum values, and saddle points of the function. So we also need to go a step above calculating the local extremums, and we need to classify these points. So the second derivative test helps us do that. So we use what we call a discriminant, and the junior tutor writes it out here. So the discriminant is just a way of testing whether or not, or to classify your local extremum. So the discriminant is given by the double partial derivative of f times the double partial derivative of y minus the mixed partial derivative of f, so xy. And so this calculates us, this helps us classify the local extremum. So if the discriminant is positive and the double partial derivative of the partial double derivative of x of the function is greater than 0, it has a local maximum. If it's less than 0, it has a local minimum. Conversely, if the discriminant is less than 0 or is negative, that means it has a saddle point, okay? So let me kind of show you what a saddle point looks like. All right, so you guys all are aware of like your local maximum, I guess. So it's like a, your vertices are like here, right? Let me use a different color. So this is like a local maximum, right? I guess like this is like a local minimum, right? That's a local minimum. Sorry, it's not black. That's like a local minimum. So a saddle point is neither a local maximum or a local minimum, and it looks like this. So there's a point. There's a point of inflection here, but there's not a local maximum or local minimum, and we call these a saddle point, right? So the rate of change at this point is still 0 at all partial derivatives, but is not a local maximum or a local minimum, and we use the discriminant to help us find that. Okay, so we calculate the double partial derivatives and use the discriminant to classify local extreme. Okay, sure. So now we're going to try to solve both of these functions together. So the first step is to, first of all, calculate its partial derivatives. Okay, so our first function here is f of xy. Maybe I can make this thicker. Let's make it like this. Okay. So f of xy equals x squared plus xy plus y squared plus y. And I'll just do a boundary here. Okay, cool. All right, so let's calculate our partial derivative first. So let's calculate f of x. All right. So f of x is just 2x. So what we're doing by partial derivatives means that we're only deriving in terms of x, okay? So any y's in there we treat as constants. So 2x plus y plus 0 plus 0, because these have no x's in them, right? All right, sure. So f of y would be 0x plus 2y plus 1, okay? Sure. So Now we need to calculate when these equal to 0. Okay, so let's set these to 0. And so this equals to 0 when y equals negative 2x. And this equals to 0 when x equals negative 2y minus 1. Okay, so we're going to sub these into each other. So we're going to sub this x into here to solve for the points where both partial derivatives are 0. Okay, so sub, I'm just going to label these 2 and 1. So sub 2 and 1, and we get y equals negative 2 times negative 2 minus 1, and that equals to 4y plus 2. Okay, we still have a y here, so this equals to y equals negative 2 over 3. Okay, so now we're going to sub this y value back into our x value, which is, I guess, over here. So sub, let's label this to 3, sub 3 into 2, and we get x equals negative 4 over 3 minus 1. Why is my x different? Huh. This should be 1 over 3. So we take our x, we sub that in, negative 4y plus 2. And then we moved it over negative 3y, and then we divided it. Okay, and then we take 2 over 3. Oh, this should be a positive. Sorry, I found my mistake. Yeah, it's very sorry guys about that. It's very easy to find mistakes when you're not paying attention. Okay, so what I did there is I added a negative when you're not supposed to add a negative, because negative cancel out here. Okay, so 4 over 3 minus 1, which equal to 1 over 3. Cool, we found our points. All right, delicious. Okay, so now that we have found our points at which both partial derivatives are equal to 0, we're now going to calculate the double partial derivatives of both, okay? So the double partial derivative is equal to 2x, or just 2. The double partial derivative of y would equal 2. And we're going to do a mixed derivative, so a mixed partial derivative. So we're going to take our f of x and we're going to derive it in terms of y, and we get 1. Cool. All right, so now that we have done that, so we have found our local extremum, which is 1 over 3 and negative 2 over 3. But we need to classify it now, right? So we need to use our discriminant. So our discriminant is, to refresh, it's this, the partial double derivative of x times the double partial derivative of y minus the mixed partial derivative squared, I think. Okay, so this equals to 2 times 2 minus 1, which equals to 3. Okay, so what does this mean now? Okay, so going back to what the junior tutor wrote. So our discriminant is greater than 0, it's positive. And our double partial derivative of x, in fact, all the double partial derivatives are positive. So we have classified that our point 1 over 3 and negative 2 over 3 is a local maximum. Okay, so let's write our concluding statement. Since d is greater than 0 and our partial derivative is greater than 0, the point 1 over 3, negative 2 over 3 is a local maximum. Okay. All right, cool. So that is the first function, okay? So let's move on to our second function. So this time I'm going to do it a little bit quicker as I went through step by step on the last time. So as f of xy equals x minus y times 1 minus x times y, okay? So we're going to expand this first. So f of xy equals x minus x squared y minus y minus xy squared, okay? Cool. We're going to the partial derivatives. So you notice here that I'm using a different notation. This is equivalent to partial over partial x, partial f over partial x. I just write f of x to signify that I'm taking the partial derivative of x in terms of x. So the partial derivative in terms of x is 1 minus 2xy minus y squared, which would be a plus. Okay. Our partial derivative in terms of y is going to be negative x squared minus 1 plus 2xy. Okay, we want to set these to equal 0. And what do we get? Okay, so we're just going to equal these two to each other because they both equal 0. Okay, so sub 2 and 1. And we get this huge equation. So 1 minus 2xy plus y squared minus x squared minus 1 plus 2xy equals to 0. We're going to simplify here. So this and this and this and this cancel out. So all we get is y squared minus x squared equals to 0. Okay. So now we have figured out that x equals to, if we move both sides cancel out, positive negative y, because we're square rooting a square, right? All right, so since x equals positive negative y, we're going to sub in when x equals y into our partial derivatives here. Okay, so let's label this to be 3. Also, let me scroll down a bit here. So sub 3 into 1, I guess. Okay. So when we sub 3 into 1, we get this equation. So let's sub positive y, okay? So 1 minus 2 y times y, so y squared plus y squared equals to 0. Okay, move this one to the other side. This equals to negative y squared, but it cancels out because this one is moved over. So this equals y squared equals to 1, and that equals y equals positive or negative 1. So we found our local extremum. So local extremum, since there's multiple, I'm just going to write it out in a therefore statement. It's going to be 1, 1, and negative 1, negative 1. Okay, cool. All right. Let's ground that. Also, let me zoom out a bit. Okay, sure. So I'm going to do the rest of the work over here. It's kind of crowded down there. Okay, so now we're going to calculate the second partial derivatives. So f of xx equals to 2y, and f of yy is going to be equal to 2x. F of xy is equal to 2x plus 2y. Okay, sure. Oh, there should be a negative. Okay, so now we're going to take our discriminant. So our discriminant is equal to, it should be negative too. No, that should be positive. Okay, this should be negative. Negative 2x. Yeah. Okay, it should be negative 2y times 2x minus negative 2x plus 2y squared. Okay, so that equals to negative 4xy minus, let's expand this out, 4x squared minus 4xy, and this should equal to plus 4y squared. Yes. Okay. Cool. So we're going to plug in our values now, our saddle points here. Let me simplify this too. So negative 4x squared plus, so this is just plus minus 4y squared, because this and this cancel out here. Let me make sure I just did my expansion right here. I don't want to make any mistakes here. So 4x squared minus 4 should be 8 minus 4 negative xy plus 4y squared. Should just be 8. Okay. So negative 8xy. So this should actually be plus 4xy. Okay, cool. There you go. So that's our discriminant. So we're going to take the discriminant at 1 of 1. And that is equal to negative 4. Negative 4 plus 4, which equals negative 4. And we're going to take our discriminant of negative 1, and that equals 4 minus 4 plus 4, which is negative 4. Okay. And finally, we're just going to take f of x at 1, 1, which is just negative 2, and f of x at negative 1, which is just 2. Okay. This doesn't really matter, but therefore, since d of 1, 1 and d of negative 1, 1 is less than 0, we have that the local extremum 1, 1 and negative 1, 1 are saddle points. So we're going to refer back up to what our junior tutor wrote. So when a discriminant is less than 0, it has a saddle point. Okay. So we noticed here that both discriminants of our local extremum yielded us negative values. So now we know that they're both saddle points, and we have solved the question. So this was a very long question, and the junior tutor got it correct. So this solution is correct. Good work. Okay, cool. All right.